So the purpose of this video is to take you through some common scenarios that we'll see in word problems in class this year. Now these scenarios tend to be a little bit specific to the early middle school years, which is where we are now. But the ideas of the scenarios that we're going to talk about are applicable beyond that too. Some of them will be re-examined when you get into algebra, when you get into geometry, when you get even up into calculus. The way that word problems are contextualized and placed into models mathematically has similarities across the entire spectrum. So even though you'll see lots more scenarios that come up in the future, these ones are sort of form the basis of a lot of the types of problems and contexts and equations that you'll be writing from word problems throughout the rest of your mathematical career. So as a quick review of the 3 steps that we use to translate a word problem into a model or an equation that describes the scenario is first to identify the unknown so we know what our variable represents. Second is to describe what's happening in the equation, not just to try to solve it with calculations, but to describe it. And the third is to substitute the variables and the numbers you know. And this video really focuses on ways that we can start to recognize patterns in this step of writing equations. So let's go ahead and take a look at a few of those common scenarios. There are going to be about 9 different word problems here. There will be a few where I ask you to pause the video and see what you can do on your own, and a few that I go through just by myself. So here is one type of equation, one type of word problem that we might see. You're trying to raise money for some sort of reason, or just money is being raised for some reason. Here you're trying to raise money to adopt an animal, and you sell cookies for $2.50 a piece. How many cookies do you need to sell to raise $50? Where our variable in this case is X is the number of cookies that we sell. And the scenario that we're looking at here is common to all types of raising money. And that's that we're going to sell things, some number of cookies in this case, for some price to create a total. So the amount of money that we raise, if you think about if you've ever raised money for something before, and you think about the process that goes on there, you have some things that you sell, you have a number of things, you have things that you sell, you have the price they're being sold for, and then when you multiply those two things together, that's when you end up with the amount of money that you've raised. So for example, the number of cookies that we sell times the cost of each cookie, that's going to give us the total money raised in this particular scenario. If we were selling pizza slices for $5 a piece and we sold 5 of them, we'd take 5 times 5 to get $25. Here, the amount of money we want to raise is $50, so that's our goal, or our total. And we're going to do that by selling an unknown number of cookies for $2.50 a piece. So 50 is equal to 250 times X. Now we can solve this equation because we know how to do that. We're going to divide by 2.5. And we end up with X is equal to 20 cookies. But the scenario that we see here is that money raised is equal to number sold times cost. Go ahead, pause the video, see what you can do with this problem here. Now there's an extra little piece on the problem, which is you've spent $30 on supplies and you want to make $110 in profit. But go ahead, pause the video, see if you can figure out how these things fit together, and then come back when you're ready to see the next type of common scenario that's related to the one that we saw before, and then we'll go on and take a look at this scenario generally and move on to the next one. So here we're still involved with the idea that the money raised is equal to cost times number sold. But we have a little bit of an extra hiccup here, which is we spent $30 on supplies and we want to make $110 in profit. And if you've heard the word profit before, the basic role of profit is that profit is the money that you have made in excess of what you spent. So if you make a certain amount of money and then you spend a certain amount of money in that process, however much you make beyond what you've spent, that is your profit. So the big scenario we're looking at here is profit is equal to the money made minus the money spent. If you've spent more than you've made, we call it a loss. If you've made more than we spent, we call it a profit. And so what we saw before with the amount of money raised being the cost per brownie in this case times the number sold is going to come into this part, now boxed in red in this equation, where it's going to become the money that we've made. So let's go ahead and put these numbers and variables into the equation. Our variable is going to be a number of brownies, because that's what we're trying to solve for. Not the number that we sell to make $110, but just the number of brownies that are sold. We want our profit to be $110. The amount of money we make, we're selling the brownies for $3.50 a piece, so that's $3.50 times X. And then whatever that amount of money is, we have to take $30 away for what we've spent, and this ends up with the equation that we're after. 110 is equal to 3.5 times X minus 30. Profit equals money made minus money spent. Another common scenario that we often see in word problems and models. Here, we have a different type of equation, taking a trip that is 224 miles long when you've already driven 59 miles. Here, the goal of this type of equation is to represent the creation of a total. So some total trip, some total number of things is going to be represented as a combination of parts. So go ahead, pause the video, see if you can use words to describe how to take what we know here to create the length of the total trip. Come back when you're ready to see this common scenario, including what the equation is, and then move on to the next one. So in this case, our total length of the trip is going to be what we've done plus what we have left. If you think about a trip as a long line that's 224 miles long, the total amount of the trip is however much you've already driven plus however much you have left to drive. So 224 miles long. You've already driven 59 miles. So what we have left, which is the unknown thing, is placed here. 224-mile trip is equal to 59 plus X. Now we can solve that equation, but right now our goal is just for writing the equation out from the word problem. Next type of scenario that we have adds a little bit more complexity to that exact same style of problem. Again, we are going to create a total trip out of what we've done plus what we have left to do. But here, our unknown is not a length, but it's a number of hours. And so we still know that our total is 224 hours. We still know that we've completed 59 miles so far. And I'm going to ask you to pause the video and see if you can come up with an idea of how we can use 55 miles an hour and hours taken to get there to write an expression for for the amount of miles that we have left. So go ahead, pause the video, see what you can do with that, and come back when you're ready to see the rest of this scenario and move on. So creating an equation that looks like this is a little bit more complicated. It goes back to that relationship that we've seen before between distance, speed, and time, where the amount of distance that you cover is equal to the speed that you're going times the amount of time that it takes to get there. So, or the amount of time that you are traveling. So here we are our distance is sort of unknown, but we're traveling at 55 miles an hour for some unknown number of hours. So if we take our 55 miles an hour by multiply it by the length of time that we're traveling, we should end up with the number of miles that we're going. So the equation that we're looking for here is 224 equals 59 plus 55x. Again, all based on the idea of having a total distance or a total value and using pieces to build up the total, because that's how totals work. It's not a bunch of subtractions down from a total to a smaller piece. A group of things or a trip is built up from smaller pieces. The next type of equation is very similar to the ones that we've done before, except this time we are looking at typing words on a paper rather than traveling down a road, but it's still a total equals what's done plus what's left. So go ahead, pause the video, see if you can take this verbal model here that describes basically what's happening in the problem, substitute the numbers and the variables into it to get an equation, and come back when you're ready to see the answers. So the total paper is 924 words long. He has already typed 168 words. That's what he's done. And whatever he has left, he's going to type at 42 words per minute, which is a speed. So it's not that he has 42 words left. The amount of the number of words that he's going to type are going to be 42 words times however many minutes he's going to type them. So we end up with 924 is equal to 168 plus 42x. Total is equal to what's done plus what we have left to do. Next one. An airplane drops 8,000 feet during its landing descent to a new altitude of 27,000 feet. What altitude was the plane cruising at before? This is not quite a total. This is not quite a this is certainly not a situation of profit and making money. And this is a type of word problem that falls under a category of start, change, finish. If we have an initial situation, in this case, the altitude is cruising at some unknown initial altitude, then something changes. It drops 8,000 feet, which is negative. And it ends up in a final situation. Then I call that scenario start, change, finish, because that's how this process actually happens. It doesn't start at 27,000 feet and raise up 8,000 to its initial altitude. It starts at an altitude, which is x. It drops 8,000 feet, and then it ends at an altitude, which is 27,000. So where it starts minus the change that happened is equal to where it finishes. And that's a scenario that I like to call start, change, finish. Two more for you to look at, and then we'll take a quick review of all of the different types of things that we've seen. Car is traveling at 65 miles an hour for 585 miles. How long does it take the car to make the entire trip? This goes back to that distance formula that we reviewed before for traveling at a constant speed. The distance is equal to the speed times time. So 585 miles of distance being traveled at 65 miles per hour for how long does it take the car? X is the number of hours. An unknown number of hours will give us an equation based on a familiar formula. Another familiar formula that we might see is the area of a rectangle. The area of a rectangle is 240 square inches. If the width is 15 inches, what is its length? That is all based on the formula area equals length times width. For a rectangle, 240 is the area. We know the width is 15, and our length is unknown. We can leave it as an L to get 240 equals 15 times L. So there are really 5 categories of problems that we've seen here. One is a sort of double category. The money you make is equal to the cost times the number sold, or your profit is equal to your income minus your expenses, the money you make minus the money you spend. Anytime that we're raising money, one of these will probably be related to our problem somehow. We also looked at some situations where we are building a total from the ground up. So we have a total number of miles that we need to travel, and we're breaking it into smaller pieces that all are brought together. We have a total number of words that we need to type, and we're breaking it up into smaller pieces that all get typed together. We also have some situations like the airplane, where our process basically goes start, change, final. We start somewhere, some change happens, and we end up at a final altitude. We end up at a final value. And if that's the case, then we should follow the steps of starting somewhere, making a change, and then ending at the final. And finally, our certainly going to come up in some circumstances where the formulas that we need are actually familiar. The area of a rectangle, the distance formula, maybe the perimeter of a rectangle, something like that. These show up a lot in higher level math classes because we take formulas that we've seen and then we manipulate them to talk about what we want to. But that was a not quite as quick as I was hoping for, but overview of a lot of types of scenarios that we might see in word problems during your work in class. And so those are the 5 categories that we tend to see this year.